Hi, this is Aziz Khan with you. So this is lecture 10 of my basics of microwave propagation. And in this lecture, we will learn about the signal diffraction. As I was given in the last lecture, I gave you a kind of introduction that now we will go in the deep things. But still the deep has, there is not a one deep. There are different type of deeps. So in every video, I will not take you to the most deepest part. So that I don't want to drone you. Uh, we will go step by step. And if you or anyone has any question, or he has some kind of, because I try to take it in a way that most of the people who are listening to it, they can understand something. I'm not making it for example, for people who are doing kind of PhD in microwave signal propagation, and even I'm not making it for anyone who does not know anything. My audience, I believe, are in somewhere in between. They know something, but they don't know something. They want to learn something. So I will start, like in the last video, I say that we will start the deep part, and we will start now to learn what is the diffraction. So diffraction happens in many ways. As I told you that the waves have diffraction. The wave can be any type of wave. It's if it is a light wave that you can see, if it is a water waves, because water also has waves, and if it is a microwave. But as we know that, like for example, water is a different kind of thing. Water is has some other properties as well. But still, water also shows us some wave structure, and the wave structure or the background or the principle is almost same. So the light also, because we can see light, and because light is used in our daily things, we use light in many ways. So light also shows us some wave principles. So first we will try to learn a bit about how water or light shows us some wave structures, how diffraction is, how we see diffraction in light or how we see diffraction in water, and then we will go to our main thing, to microwave, that how we do it in microwave, and then I will show it to you on the tool as well, because it was our main thing. If that I will show it to you on the tool, that how we calculate, how we can manipulate something, how we can make something out of it. So first thing first we should read the principle. So diffraction of microwave beam occurs when the beam's center line grazes over an obstacle and RF energy reaching the far end is attenuated. So in microwave, what happens is that, for example, these are your two antennas, for example, one is this, one is this. And assume that something comes in between. Like, for example, this is an obstacle which comes in between. You have one antenna here, one antenna here, and something comes in between. So, and it comes on a position where your main microwave link, main lobe is almost hitting the top part of the obstruction. It's grazing over the obstacle. So the far end becomes attenuated. And how much it happens, path loss can calculate it. So diffraction creates a small shadow region where some energy is redirected in a narrow and rapidly diminishing wedge towards total shadow. So, so this I will show you in the next slide. But let me first take you to the normal diffraction that we see in in nature. Like for example, this first picture. Just assume there is a laser light at this point, because I have only two hands. So, for example, this is our this is what you called is so for example, we have a beam, and this beam is pointing to this plate, but between this beam and this plate there is another plate. and this plate has a small circle in the middle of it, and the beam is passing through this circle. So as I told you, this is the beam, and as it says also that there is a red laser beam projected on a plate after passing through a small circular aperture in another plate. So you have two plates side by side, I mean very near to each other or a bit far. One plate has a aperture, and the light is coming from behind this plate somewhere here, and it's passing through this aperture, and then it's being projected on this plate. So what will happen, as you can see here, there should be a big center, and then there should be waves around it. So a single source of light, it makes some, some secondary waves were created somehow, which some at some point they combined and some point they destroyed each other. So we have exact circular pattern of waves. Similarly, if you see here, this is a kind of sea, I mean, and there's a small opening because we know that sea has some waves. I mean, sea is not static, it's going up and down a bit. Because of it, and when it passes through this narrow slit, then you can see the waves are being created, I mean, at this place. Here also it shows that, for example, this is a pool, and you put two things which are creating ripples. Like, for example, you are doing it with your hand, like you are patting on the water and it's creating waves. So these two waves, they also combines at some places, and they destroy each other on some places. So this is how in light or in water this happens. In microwave, it don't happen exactly the same way, but quite similar. The difference, as I have told you, that here there are some natural limitations. I mean, in microwave, the problem is that there are two antennas. The upper part, I mean, if there are two antennas and something is in between of it, so your microwave is coming from one point and going towards one another point, but the upper portion, I mean, everything on upper side of it is open, I mean. But here the slits or the openings are on the exact place. I mean, they have nothing is open kind of thing. I mean, let me show you. Hopefully, it will give you some more idea. So for example, you have an antenna here and you have another antenna here, as I was trying to show with my hands. And something, I mean, a small mountain is in the middle of it. And we call it knife edge because if you see here, we generally assume, if you will see on the maps as well, most of the mountains, they are usually knife edge type. That's why knife edge is very popular. Now here if you see the upper portion of this, it has no limitation. I mean the upper side is fully open. The below side, or I mean the side towards the ground, it can be obstructed, but the above side cannot be obstructed. So whatever is coming from this direction is kind of obstructed from here, and from the upper part it's fully open. And if you put your antenna somewhere here somehow, then it will be able to get the direct line of sight region. But as we saw here that when it passes or it grazes something, then we have kind of secondary wavefronts are created. Like if you see here, just as this microwave reaches this point, another wavefront is created. And now these two wavefronts, what will happen is that at some point, like in this area, they will be either adding to each other or subtracting to each other, and they may be creating some nulls and some highs at some places, I mean. But the down area, this area, as we can see, this direct wave is going directly, but this diffracted wave, it is coming here without any interaction of the direct wave. It is coming alone, I mean. So in this region, what will happen is that you will have a diffraction loss here, which may be any number, and I will show you that how we calculate it on path loss. But the point is first to make you aware that what kind of situations generally create a diffraction loss. I mean, every situation don't create a diffraction loss. We will have to see that as well. So usually kind of knife edge type of thing, or if you have some forest type of things, they can create some kind of diffraction. Let me take you to path loss, and like this is one of our link. Let me see if I have it open somewhere. Yes. So for example, this is a link, and I have put some things on it so that we can see. Let me remove some part of it. Like let me remove this. Let me remove this structure just to make it a bit clear for our start. Let me remove this as well. Okay. Now assume that this is this is a normal link. We go to antenna heights. Your antennas are fine. They have no problem. And when I go to diffraction, and for example, I ask it to give me diffraction with respect to second antenna. So it says that you will have some diffraction loss for the first 23 meters, but then it will be zero. Let's see why it's saying that we can have it for first 23. So we can see that hopefully maybe this is coming, because our zero is here. So almost 23 meter, first 23 meter are behind this thing. So this is, you can say this is our first knife edge. This is a kind of knife edge which is creating this all. Let me show you again. So you see there's a 21 dB which is going down to zero. Let's try to correlate it. Okay. So this is, let me try to now give you the background of it, that why we see that. Just assume that your waves were coming from this direction, and this was the knife edge in between. So what we will assume is that, like for example, some of the waves will be blocked here. This is our zero position. So anything above this zero, which is on -1, -2, will get the actual wave, and the things below, the things which are on 1, 2, and 3. If you see here also, this is -1, -2, and here it is 1, 2, and 3. So we expect, this dotted line is the expectation. We expect that from -3 somewhere here up to 0, we will get some wave, somehow. Here it is shown as 0, but whatever, it will get some wave. But as soon as we go behind it, as soon as we are down from this level, we assume, because now every wave is being stopped. This should stop the waves. So it should go to zero. It should have the most kind of power attenuation. But in reality, this is the real curve, which is kind of a bit similar to this curve. They are only, the difference is that they are in the reverse of each other. This is from zero, and it is basically going down from here. Here only the problem is that it is going down in this direction. So in reality, what will happen is that when you are in this region, you will get the waves. But when you go in this region, which is a kind of shadow region for us, the shadow region will not dramatically or suddenly go to zero, but it will have a very high diminishing of power, but still it will have, like here it will show you only -5 dB. Here it will show you only -10 dB of attenuation, -15, and it will go down slowly. Just like here, when you are on 5-meter height, you will get a 21 dB. But when you are on 10-meter height, you will get for example, 17 dB attenuation. Like on 15, you will get some value 20. But from 25, you will get zero diffraction loss. Just like here, when you are in this area or you are in the above area, you are higher than this obstacle, then you will not get any diffraction loss. So this is depicted similarly in path loss as well. Path loss also shows you exactly same or similar kind of picture. Now let us just see that what kind of things change this value. I mean, like right now, just keep this in mind. I mean, if we don't put any extra information here, then we get something. Let's add information and let's see that what kind of difference it brings. So let me go to terrain data and let me start adding. For example, let me start from here. Range of structure, I will say that it goes up to the last point, and for example, it's 12 meter. So I added something. So after adding this, let me go back to my diffraction. You should keep the previous picture in your mind that from 21 we were going down, and after 25 meters it was kind of flat. Now let's see. We have the same values. Let's plot it. Now you see it does not start from here like the previous one. The previous one was like this. It starts from here. So it means that this red is because of the ground thing. This green is basically because of this vegetation. So this green has added almost 45 dB extra diffraction. So your diffraction starts from 65 dB now. You will have 65 dB attenuation at this point, and it will go to around 34-35 meter, and then it will be flat up to 90 meter, I mean, and the flatness is also almost 17-18 dB or 15 dB. So it is telling you that as per your current scenario that you have provided, you should put antenna at almost 35 meter on this side, and still it will have a 17 dB attenuation. It will not have a 0 dB attenuation. So this is what it is kind of telling you. And how we, for example, if I say that, okay, I want to make it part of, for example, let me show you here. This is the terminal analysis. So you see that it has added this diffraction of 14.9 based on the antenna heights that we have. And just to show you that how we can manipulate it. So for example, if I remove this from here, if I delete this and then I go to transmission analysis, you see now diffraction is 0. So it is automatically calculating for the time being. I will show you that part as well. I have asked it to automatically calculate it every time. So that's why when I make any change, it is deflected. It is shown you at the spot, I mean. Receive signal is -24. Let me add it back. Range of structure. The second point is here. It's 12 dB, 12 meter. Close. So you see 14.9 added. So from -25 almost, it reaches -39. So whatever is coming, it is shown to you at the same time. Let me add one more thing just to make you a bit more aware. For example, at this place, let me add a single structure of a building. I make it a height of 12 meter and I add it. So now I go back to diffraction and I go to this point. I calculate it. So we see that it has not brought any bigger difference. So let me make it a bit more. Let me make it 20 meter. Okay. And then I go to diffraction. Now you see this point is shifted a bit. I will remove that and I will show you again. This point is now on almost 42 and a half. This point is shifted and its height is I think almost same 15, but let me show you. So now it's a 24 dB loss because of the trees and the building. So you can see that, I mean, whatever we put, it has some kind of effect. And let me show you one more thing. Okay, what are the parameters? And Let me go to module transmission. Okay. So if you have some values, you can directly change this also if you want. I mean, it's not very much recommended. It's better that you ask path loss, but you can see here it's calculating it on different. Currently, it is on K is 1.33, but you can change it to different values and you can see the effects. I mean, that when you change the K value, the effects change at the same point. And no, I don't want to make any changes. And one more thing that I wanted to show you is module diffraction parameters. So it was automatically calculating for 4 by 3 because I have put it like this. You can remove it or you can keep it. It's up to you. Then there are some more parameters. Again, as I was telling you that I will go deep, but a bit slowly. I will not go in too much deep on the first day. I have other slides. I will keep talking about diffraction for some more time. I mean, so I will show you other things. But just to give you some idea that the algorithm, it will use a path loss own algorithm. Troposcatter method is auto. What kind of climate region it is, you can select from here. Polarization is horizontal vertical frequency. Tree type is generally what type of tree you feel are in the area. So I will not go in very much detail of it right now, but frankly, I mean path loss, because you know everything just we saw as well. If you remember here, let me take you again just for a. You saw here also that even for this value, if you change the k value to different things, the actual value changes. So what I wanted to say is that everything will change your values. I mean, you uh, like if you change anything from here, it will have some kind of effect on the final value. Like for example, if the foliage is wet or dry, I mean, we know that the dry foliage has low loss and the wet foliage has a bit higher loss. So everything that you know of the area, and that's why in most of my video I try to emphasize that the local knowledge of the area is very important. For example, I'm a normal guy. I live in Pakistan. I personally know by newspapers or other thing that, for example, Indonesia has a lot of rain. But maybe I don't know. I mean, for example, maybe Indonesia is too much big, and some part of Indonesia is somewhere where it don't have a lot of rain. I mean, maybe. I mean, I'm not saying that I'm saying right or wrong. I'm just giving you an idea that, for example, I am in Pakistan. I mean, okay. So I know that Pakistan has no general value. I mean, the north areas of Pakistan has very low rain. They have snow. I mean, snow is very much different than rain. Then Pakistan, the south is very different. I mean, it's a coastal area. In the middle, there is some very fertile land which has a lot of rain. But in the same middle, we have some desert as well. So I know about Pakistan. I know in very much detail, I mean, about Pakistan. I know that in which area I should put which kind of values. So similarly, if you are from any area and you have some idea of that area, so you should work accordingly and you should put your local knowledge in it. That is very much required. I hope that I have given you a kind of point for that. So let's go towards finishing it. I hope that it was not too hectic. I mean, you should have learned something out of it. Let me give a bit of recap that we started from telling you that what actually is diffraction. We learn a bit about light diffraction, water waves, and then we jump to the microwave. And we tell you that in microwave, most of the time we take the knife edge as an example, and I showed you that theoretically we have a diminishing curve which tells us that if we have a diffraction, then based on the antenna height or based on its value in relative to the ground, the attenuation increases. I mean, as more you are towards the ground, the more diffraction you may have. As more high you can go, the less diffraction you generally have. And we see that in path laws as well, that how we calculate diffraction, how we can add something to the map, how we can add values, what kind of values we should normally add, why the local knowledge is very important. So hopefully based on all that, you should have got some good idea. So if you like it, then share it with your friends as well. I'll be making the next level of things, and hopefully we will meet in some next video. Goodbye.